It's time to start one of the most amazing and quite confusing theory which was given by Albert Einstein in 1905. It is called the special theory of relativity. So before understanding what is special theory of relativity, we first need to understand about relativity and the frames of reference. So to understand this concept, let us consider a situation in which we have a tree. Let's say this is a tree, and here we have a vehicle. Let's say a vehicle is here. Now let's take a frame of reference through different axes. So let's say one axis is here, so let's say this is x, y and z axis, and let us take another axis. Let's say the axis is here. So let's say it is x dash axis, y dash axis and z dash axis. Now what let's say that the distance of the car from the first axis, first frame of reference, is x, and the distance of the car from the second axis is, let's say, x dash. So this is the situation that we have right now. Let's say that this is our axis or frame A and this is B. Now let us assume that the car is moving with some velocity, some constant velocity. So what will be the things which will be changing, what will be the things which will be same in both the axis or frames of reference? So let us try to understand that. So first of all, let's say that what are the parameters that we will be talking about. So let's say the parameters are position of car, displacement of car, size of car, mass of the car, velocity of the car, then acceleration, so let's say these are the parameters, and we will take frames, let's say A and B, and what will be the situation? Will you be in agreement or not? Will the two people in different frames will be in agreement or not? So these are the quantities, and this will be the situation, our opinion. So in the first situation, let's say both are at rest. Both A and B are at rest. So if both the frames of reference are not moving, they are fixed at their location, and if there is some a car is moving with some velocity, let's say 25 meters per second with some constant velocity, Then first of all, will the uh, will the person in different frames, frame A and frame B, will they agree for the position of the car? Will the distance of the car be same for both the frames? So obviously not. In one frame the position will be x, and in another frame the position will be x dash, so they will be in disagreement. Then displacement. So when the car moves from here to here, so the displacement will be same for both the situations, because in displacement we will be discussing about initial point and final point. So final point minus initial point will be same for both the frames. So in case of displacement, they will have same displacement. Let's call displacement d. So they will be in agreement for displacement. Size of the car, so for both of them the size of the car, let's say the size of the car is L, the length of the car or size of the car is L, so they will agree that the size is same. In both the frames you will see that the car is of length L, no problem with that. Then mass, so in both the frames mass will be same, and they will be agreeing that mass of the car is same. For example, if the mass of the car measured from this frame is 1000 kg, so from the second frame it will also be 1000 kg. Then the velocity of the car, so they will observe same velocity, let's say 25 meter per second from both the frames of reference, because the displacements and times are same. What about acceleration? So they will also agree about the acceleration. If the car accelerates, they will agree that it is accelerating with the same value. So these are the things when both the frames are at rest. So this will be the situation. This was explained by Galilean theory, explained by the Galilean theory of relativity, Galilean relativity, in which Galileo and Newton considered space and time to be absolute quantities, that is space, that is time is same at every place, it does not change for anybody. Similarly space, so space and time were considered to be absolute. Now let's consider a similar situation, but this time the frames, one of the frame will be moving. So say let's say the situation is that A is at rest and B frame moves with constant velocity, let's say 20 meter per second or 10 meter per second. So this is the second scenario. So will they be agreeing or disagreeing on various factors? So they will be agreeing on the same thing will be there: disagreement on position, agreement on displacement, agreement on the length, agreement on the mass, but they will not be agreeing on the velocity. Okay, because in the frame of reference, which is stationary, car will be moving with 25 meter per second, but in the second frame the speed of the car will be only 5. Why? Because frame is moving with 20, car is moving with 25, so the relative velocity will be 5. So they will not be agreeing on the velocity of the car. So let's say velocity will be v and v dash, and they will disagree. Now acceleration will be same for both, so they will be agreeing for the acceleration. So this is a situation which was explained by Galilean transformation or Galilean relativity, in which space and time were considered to be absolute. Okay, and obviously here F equal to ma will be followed, and here also F equal to ma will be followed, because the acceleration is uniform. Okay, whether 0 or uniform, so F equal to ma will be followed according to Galilean transformation when the space and time are considered to be absolute. But what Einstein observed through his theory was something different. According to Einstein, the space and time uh, are not absolute. According to Einstein, space and time are not absolute. Now let's say the situation is A is at rest and B moves with some velocity. But this time the velocity is very high. Let's say the velocity is 2 into 10 to the power 8 meters per second. So when the velocities are very high or close to the speed of light, then it is observed that space and time are not absolute. That is, nothing will be here absolute and nothing will be same. Position of car will be different, displacement of the car in different frames will be different, sizes of the car will be different, mass of the car will be different in different frames, velocity of the car will be different in different frames, acceleration of the car will be different in different frames. So they will be disagreeing on everything. So it was observed by Einstein that when the velocities are very high, then in that case the space and time are not absolute. Time is different at different locations and it depends on the velocity of the object or the thing. So this is called the Einsteinian relativity, and this will be the main topic of special theory of relativity. So according to Einstein, space and time are not absolute, and according to Galileo and Newton, space and time were absolute. Time is same everywhere in the universe. uh, but Einstein observed something different. So now you will understand why they are different by by understanding the frames of reference and the various quantities and formulas that we will be finding out. So you will understand what we are trying to discuss here. So let's start with the discussion. Let's first try to understand few terms. So first term is event. So what is the meaning of an event? So event is any occurrence in space time. Okay, when and where. Event is any occurrence in space time, when and where. Frame of reference. So frame of reference tells us about the coordinate of space and time. So frame of reference is a reference with respect to which we measure an event's space and time. A reference with respect to which we measure an event's space and time coordinates. For example, here this xyz was a frame of reference. So from this frame of reference we found out the position of the car or the velocity of the car. Okay, so frame of reference is a reference with respect to which we measure an event in space and time coordinates. Now there are two types of frames of references. One is called the inertial frame of reference and one is called the non-inertial frame of reference. So the inertial frame of reference is the frame of reference which is whose acceleration is 0, A non-inertial frame of reference is a frame of reference whose acceleration is not zero. Okay, that is, here either the frame is at rest that is velocity 0, or it is moving with uniform velocity, that is velocity is constant, its value will not change. But in the case of non-inertial frame, the velocity of the frame will change. The direction can be changing or the magnitude can be changing. So in inertial frame of references, Newton's law are valid. They can be applied as it is. But in non-inertial frame of reference, Newton's laws are to be modified. Newton's laws are not valid. They are to be changed or modified. Now these are two types of frames of references. In special theory of relativity, we will be only concerned with the inertial frame of reference. We will be not concerned about the non-inertial frames of references. So this is the important thing you need to keep in mind, that inertial frames will be discussed in special theory of relativity. And when we go to the cases of non-inertial frame, then in that situation we will be discussing about the general theory of relativity. So this is special theory of relativity. So the idea of special theory of relativity was first Einstein came up with this idea because of one experiment. That experiment was called the Michelson-Morley experiment. Michelson-Morley did an experiment in late 1800s in which they were trying to find the velocity of light or speed of light, and they found something amazing. What they found is that in their experiment they found that the speed or velocity of light in vacuum always remained same. Okay, that is, however, in whatever direction and in whatever situation they tried to measure the velocity of light in vacuum in space, they found that the velocity of light came out to be same, and its value was approximately 3 into 10 to the power 8 meters per second. So this was the approximate value that they calculated. So no matter what, the velocity of light always came out to be this. So this was quite confusing, because let's take a situation. Let's say this is object A, which is moving with velocity 20 meters per second in this direction, and let's say this is object B and it is moving with 30 meters per second in this direction. So if you are on object B, if you are here, so what you will observe? You will observe that the velocity of A will be equal to 50 meter per second if you are inside B, because for you this is at rest. So for you will see that A is moving with 50 meter per second. And let's say if situation is like this, it is moving with 20 meters per second and it is moving with let's say 30 meters per second, or let's say 40 meters per second, both in same direction. So if you are in object B, frame reference B, so velocity of A will be 20 meter per second for you, because you are moving with 20 meter per second in the same direction as A. So you will observe less velocity for A. So the velocities change, okay, if you are moving towards or moving away from the object. But in the case of light, or we should say EM waves, the speed always came out to be C, approximately equal to 3 into 10 to the power 8 meters per second. So no matter whether the object was moving towards the light or moving away from the light, the speed always came out to be 3 into 10 to the power 8 meter per second approximately. So this was quite unbelievable, because the speed must change whether if the object is moving towards the light or moving away from the light. So ultimately this was the starting point for special theory of relativity. So Einstein thought that if this experiment is correct, then if the speed of light is a universal constant in vacuum, then we need to let go of our notion of absolute space and time. So according to Galileo and Newton, space and time were absolute, but Einstein thought that if speed of light has to be same, then the space and time cannot be absolute. So what does this mean? Space and time are not absolute. You will understand when we discuss a few things. So what are the postulates of the special theory of relativity? Postulates of special theory of relativity. First postulate is about the universal velocity. So according to this postulate, Einstein said speed of light in vacuum is a universal constant. Approximately equal to 3 into 10 to the power 8 meters per second. And this was also confirmed by the mathematical equations of Maxwell. In Maxwell's equation, it was found that the speed of light in vacuum is given by this formula, 1 over root mu naught into epsilon naught, where mu naught and epsilon naught are constant values. So once we put their values, we found that the value is approximately 3 into 10 to the power 8 meters per second. So according to Maxwell, the mathematical value for the speed of light in vacuum can be found out using this. So Einstein was a firm believer in electromagnetic theory of Maxwell. So he proposed that if Maxwell's theory is saying that, and also the practical of experiment of Michelson-Morley is stating that the speed does not change, so this means the velocity of light is a universal constant. Now the second postulate was that the equivalence of inertial frames. The equivalence of inertial frames. So what does this mean? So according to this principle or this postulate, the laws of physics are same in all inertial frames. All inertial frames are equivalent. What does this mean? So this means that the law which is applicable in one inertial frame will be applicable in any other inertial frame. All the inertial frames follow the laws of physics as it is. So this was another important postulate. So after this, let's understand various formulas that we have for finding out the different velocities, time periods, different situations in the case of special theory of relativity. So in order to understand this, we need to understand the Lorentz transformation. Lorentz transformation. So, and there is obviously Galilean transformation as well. So let's try to understand the formula for both Galilean transformation and Lorentz transformation, so that you can compare between them. So first of all, let's start with the Galilean transformation because it is simpler. So let's say that we have two situations, two frames of references, okay, just like we started, okay. So let's say one frame of reference is here, y, x and z, and another frame of reference is here, y dash, x dash, and let's say z dash. Now let's again consider any object like this. So the distance will be x1 of the closer part, and of the far off of part it will be x2, okay, and here distance will be x1 dash, and of far off point x2 dash. Now let's try to write the Galilean transformation equations. So first we need to understand the position. So x dash will be equal to x minus x plus vt, where v is the velocity of the frame of reference. This frame of reference is moving with velocity v. So x dash, that is the position x, will be equal to position by first and the velocity into time of the frame of reference, and if it is moving in different direction, then it will be minus, okay. Now next is y dash. So as the frame is only moving in x direction, so y components will be same and z components will be same as well. And according to Galilean transformation, the important thing is time components will be same, that is time will be passing equally in both the frames of references. So this is the main part of Galilean transformation. But according to Lorentz transformation, if we have the similar situation, so let's say we have a similar situation, and it is moving in some velocity. So in that case, what will happen is that Lorentz transformation say that x dash will not be equal to x minus vt only. It will be equal to x minus vt over root 1 minus v square over c square, where v is the velocity of the frame and c is the speed of light in vacuum. Now again here y dash and z dash will be same because the frame is only moving in x direction. But amazingly, time will not be same here. Time will be t dash equal to t minus v x over c square upon root 1 minus v square over c square. So the time period will not be absolute and space will not be absolute. So this means that in according to Lorentz transformations, which were used by Einstein to give the theory of special theory of relativity, the transformations of position and time in different frames of reference is given by this, where remember this x is the displacement, okay, or the position from first frame of reference. So this is the difference between Lorentz and Galilean transformations, and using this Lorentz transformations we will now be finding the various things like length contraction, mass increment, time dilation, etc.